Hey guys, today I wanted to show you how to do a potential energy scan calculation using ORCA, and also that would give us an example of how and why would someone need to use dummy atoms. So let's start, and to begin we will look at the today's featured reaction, which is Diels-Alder cyclo addition. So you have two molecules coming together, forming a cycle. You have the diene and the dienophile. And when you look at this reaction kind of in 2D, it really looks like the dienophile just slides in and the cycle is formed. However, if you look at the 3D structure of the transition state, then we see that the actual the molecule are actually kind of piled up on top of each other, so that the pi systems can interact well. So the goal of the calculation that we'll be doing today would be to determine where exactly should these two molecules be placed with respect to each other to be the closest to the transition state. We will define this path and scan along it, and then check for the energies at every point on this path. So the first thing that you have to do is to optimize each reactant separately. So this is my diene, and this is my dienophile. So these are the already optimized structures. And now what I have to do is basically put them together in the same system and then scan along a predefined vector. So you can just select this molecule, copy paste it into this one, and I'll just show you kind of the end result of that. So I placed my molecules kind of like this, staggered one on top of each other. And you'll notice two big pink balls in the middle of my two molecules. So I placed them there because these are borons, if you're wondering. So I will transform these two molecules into dummy atoms. And why do I need this? I need these two molecules because I want to define a vector that connects these two molecules, and I will scan along this vector for my scan. So something like this. All right. So this is needed because for the potential energy scan, you can only scan along one vector at a time. And for Diels-Alder, for example, you would have to have several, so you'd have to go from the middle of this bond to like the middle of this bond, and you can't go from bond to bond. You have to go from atom to atom. That's why I have those virtual dummy atoms. They don't take up any space and they don't have any electrons. They're like just really points, virtual points in space. So I use those two virtual points to define a vector for ORCA to follow and calculate the energy along this path. So now I'll click on extension, ORCA, generate input, and please in the format select Z matrix compact, and it will give you this format of the atoms, and then in the end add a star because it's the end of the input, and then you're ready to click on generate input. So the kind of command line would be this one over here. So I used a DFT with this specific basis set. And well, you can use anything you want, really. That's not the point here. The important part is to add this section over here where we'd scan and constrain our geometry. So in this geom section, the first part is the scanning. So we're scanning a bond. So you put the B, and then you put the number of the two atoms that we're scanning. And here is an important thing that we have to really be careful with, is that in ORCA the atoms are labeled starting from 0, not from 1. So whatever number you see here in the label in Avogadro will actually become this number -1 in the ORCA program. So if we have now dummy atom 9 and 10, in ORCA they will become 8 and 9. Alright, that's why I have B8 and 9 here. After the equal sign, I put the maximum distance, so the distance that they are at now, and then the minimum distance, and then the number of steps that I want the program to take to go from one to the other. Then I added the end keyword, which ends the scan section. The next section in the geometry part is the constraints. So because we don't want the dummy atoms to go like wandering around your optimization and jumping from place to place, I need to confine B9 between C1 and C2, and B10 between C4 and C7. Once again, the labeling is whatever number you have -1, and you end up with these constraints over here. I'm just going to zoom in so you can see better the format. It's in curly brackets, and the C stands for constraint. So when you're done with the constraint section, you also have to add an end key, and then you need another end after to complete the geometry section. All right. Now, the last tricky part for the input is the fact that this format over here, as the compact Z matrix, is actually not recognized by ORCA. Neither is the other Z matrix format that they provide in Avogadro. That's why I had to write a script in Python to transform this into the format that is recognizable. You can find this script on the GitHub under my username. I'll give the link in the description of the video. And the script is called convert to Z matrix. So you just type in your command line python space convert to zmatrix.py space the name of the file, hit enter, and then it will spit out the same file, but in the end, at the end of the file, you will get the right format. Okay, so now I can just copy this and replace this here, and now I have the correct formatting. Also, I have replaced boron by the two letters Da, because these are dummy atoms and not borons. If you have boron, the boron has electrons and it takes up space, so your optimization will go completely nuts. So don't forget to change your dummy atoms to Da. So now we're ready to proceed. And let's check the output. I'm just gonna close this. Alright, so now if we open the trajectory file from the scan, don't forget that the trajectory file is not read by Avogadro. You just have to change the extension trj to xyz, basically just renaming. So I already did that. So I'm just going to open it here. And now we will be able to see how our scan progressed. So notice that the dummy atoms now became those little black dots because they're actually not atoms, they're just points in space. Now I can go into extension animation, and let's play our loop. Now you can see that at every single step of the scan, ORCA optimizes the structure, and when it's happy with the result, then it jumps to the next distance. All right, so this is how the scan goes. Now I also want to know the energy of the conformations along this path. For that, you can use the script that I provide here. It's called plot energies. So you would just run it on your .out file. And you will get a picture that looks somewhat like this. On the bottom is the number of step, and on the left is the energy. So if we were looking at finding the conformation or the distance between our molecules that would be the closest to the transition state, we will be looking somewhere in this region over here. So I think that's it for this tutorial. I hope it was clear and useful, and I will see you next time when we will do a transition state search and optimization.